You know, we're all taught pretty early on that light travels in a perfectly straight line. But what if that wasn't the whole story? What if I told you that sometimes light can actually bend around corners? Well, today we're going to dive right into this bizarre and pretty beautiful phenomenon. All right, so here's our game plan for tackling this mind-bending idea. First off, we're going to get a grip on what diffraction even means. Then we'll head into the lab, metaphorically of course, for the classic single-slit experiment. We'll try to solve the puzzle of how light can create darkness and then see how it bounces back to make bright spots. And finally, we'll look at how physicists can actually measure these wild patterns. Ready? Let's get into it.
So, first things first, what do we even call this weird behavior of light? Let's start with the absolute basics.
It has a name, it's called diffraction, and the basic idea is actually super simple. When a light wave smacks into a sharp edge, it doesn't just stop or sail straight past it. Nope. It actually bends and spreads out, and that bending is the key to this whole mystery we're unpacking today.
Okay, so how do we actually see this happening? Well, we use a classic setup from physics class, the single-slit experiment. It sounds simple, right? We just shine a light through one tiny little opening and see what happens on the other side. The results, though, well, they're anything but simple.
So here is where it starts to get a little wild. That slit isn't just a simple doorway for light. As the light wave squeezes through, every single point inside that tiny opening starts acting like its own little light source, sending out new waves in all directions. It's the way these new waves all mix together, how they interfere with each other, that creates the incredible pattern we end up seeing.
And that right there explains the big bright band we see right in the center. All those new little waves traveling straight ahead have the exact same distance to go. So they all arrive at the screen perfectly in sync. Their crests line up with crests, their troughs with troughs. They basically team up, reinforcing each other to create the brightest spot of all. Scientists have a name for it, the central maxima.
A bright spot in the middle? Okay, that makes sense. But this is where things get really, really weird. Let's talk about the most puzzling part of this whole pattern, the dark bands.
I mean, seriously, think about it. This is the big question, right? How is it even possible to take light, add more light to it, and end up with total darkness? It sounds like it should be impossible, but it's actually at the very heart of how waves work.
The answer has a name, destructive interference. It's what happens when the peak of one light wave runs into the valley of another. They just cancel each other out. And this formula you see here, it's basically the treasure map that tells us the exact angles where this perfect cancellation is going to happen, creating a dark spot. Okay, let's walk through this for the very first dark fringe. Imagine we divide the slit perfectly in half, a top half and a bottom half. Now, a wave from the very top of the slit has to travel just a tiny bit farther to reach a certain spot than a wave from the very middle. And if that extra distance is exactly half a wavelength, bam, they arrive perfectly out of sync and cancel each other out completely. And this doesn't just happen for those two waves. It happens for every matching pair of waves from the top and bottom halves. The result? Total darkness.
So what about the next dark fringe? We just do the exact same thing again, but this time we divide the slit into 4 equal quarters. The waves from the first quarter cancel out the waves from the second quarter, and you guessed it, the waves from the third quarter cancel out the waves from the fourth. Again, every single bit of light finds a partner to cancel out. Boom, another dark fringe.
And just like that, we found a simple, powerful rule. To find any dark fringe, the first, the second, the 10th, you just divide the slit into an even number of parts. The waves from each section will always cancel out the waves from the section next to them. And that's what creates the darkness.
Okay, we've cracked the case of the dark fringes, but what about those other, dimmer bright spots on either side of the center? If all this cancellation is going on, how does any light survive to create them?
Well, this is the really clever part. To get the first bright fringe, imagine we split the slit into 3 parts this time. The waves from the top third and the middle third, they do exactly what we saw before. They cancel each other out perfectly. But that leaves the bottom third all by itself with no one to cancel it. And that leftover light is exactly what we see as the first bright fringe.
And the pattern just keeps going. For the second bright fringe, we divide the slit into 5 parts. 4 of those parts pair up and cancel each other out, leaving just the bottom fifth of the light to make it to the screen. And that's why each bright fringe gets dimmer as you move away from the center. A smaller and smaller fraction of the light is actually left over.
So now we have our second rule of thumb. For any bright fringe, you just have to divide the slit into an odd number of sections. Most of them will cancel out in pairs, but there's always that one extra unpaired section left over to create the spot of light. Simple, right?
All right, we have totally built this thing from the ground up. We get the dark spots, we get the bright spots, we understand the whole pattern. Now let's bring it all home and see how this lets us actually measure and predict what we're going to see.
And this right here is the payoff. All of that theory, all that business with dividing up the slit and pairing off waves, it all gets boiled down into these powerful practical formulas. If you just know how wide your slit is and what the wavelength of your light is, you can calculate exactly how wide that big central bright fringe is going to be. And that's really what science is all about, isn't it? Turning a weird, curious observation into something you can actually predict and measure.
So let's do a super quick recap. 1. Diffraction is just the bending of light. 2. A single tiny slit acts like a whole bunch of new light sources. 3. The interference between all those new sources creates the pattern we see. 4. The dark spots happen because of total cancellation. And 5. The bright spots are just the leftover light from partial cancellation.
So a single, tiny slit. That's all it takes to turn a simple beam of light into this amazing, intricate dance of light and darkness. It's a spectacular way to see the true wave nature of light. Which, of course, leaves us with one last, nagging question. If a single slit can create a pattern this complex, what in the world happens when you use two?